VRF or VRV is my world, right? So it's what I've specialized in for the past 11 years in our industry. This is a very relaxed class, guys. So this isn't like we're going to sit down and we're going to fill out handouts and we're going to go through service procedures and guidelines. This is a introduction class. So I want you guys to ask the questions. There's no such thing as a stupid question. I want you guys to ask the questions that you've always had about VRV or VRF. I want you to sit there and actually think about what we're talking about here and how it relates to your normal service call, to your normal installation, what hangups you might think of, or just in general, queries. This is nothing about structure. I literally threw 7 different presentations together just for this introduction class, just to cover on a very broad category what this is, what's so fancy about it, why this is not complicated. This looks complicated now, right? What you see here on this board, a heat recovery system with 3 indoor units and 3 branch selector boxes. But at the end of this class, you're going to see this as just a normal split system. That's it. That's the whole purpose of this class, is to break down the concepts to show you that this is just air conditioning, right? This is just superheat, subcool, discharge superheat, right? It's a split system. It's a little more complicated than that. But when we break down the components and I show you what they're actually doing, you're going to know that this is just a split system. It's going to give you a little bit of confidence. That's also the purpose of this class, is to build some confidence. As technicians, right, we always have those scares. And we go out in the field and we see something new for the very first time, and you kind of get that, I've never seen this before. And then you call your service manager, your service coordinator, and you say, why the heck did you send me on this call, right? I have no clue what I'm doing. I have no clue what I'm looking at. After this class, you're going to know exactly what you're looking at. Does anybody know what VRF or VRV stands for? Extra points if anybody knows what they both are.
Variable refrigerant flow.
Yes. So VRF is variable refrigerant flow. VRV is variable refrigerant volume. Everybody says, well, they're the same thing, and technically they are. I fought that good fight saying they were different for many, many years, and I finally just gave in because it's true. They are the same thing. The only difference between VRV and VRF is that Daikin invented the technology that is VRV. And so when you're the first to the finish line, you get to call it whatever you want to, and you get to stamp that big copyright on it, and you own it now, and nobody can copy it. And so Daikin Systems will call it VRV. The rest of the world calls it VRF. Essentially, I wouldn't say it's copy technology, but they came up with it first, way back in the 80s, and now we have it today. So this technology has been around since the 80s, 1980. Right? This company's been in business. Daikin, they're actually celebrating their 100 years this year. But this is not new technology. It's been here for a long time. So let's go over the basics. Everybody on this call hopefully understands what superheat is. We take suction pressure, convert it to saturation temperature, subtract it from suction temperature line, right? We get superheat. Subcooling, right? Liquid line temperature, liquid pressure converted to saturation temperature. Discharge superheat, discharge temperature, subtract it from saturation temperature. This is all normal stuff. The picture you see here in front of me is pulled from Daikin's slide deck of residential systems, right? I am showing you that the things we check on a residential system, everything you see on this screen, is the same thing that is in a VRF system. Same thing that's in a VRV system. We haven't changed it. There's a few extra components between, the indoor unit and the outdoor unit. There's a few extra components between the compressor and the condenser, between the condenser or outdoor heat exchanger and leaving the actual outdoor unit. But it's all the same concept, guys. All right, so we've talked about it a little bit about we know what the name is now, right? Variable refrigerant flow. Let's break it down. Variable refrigerant flow just essentially means the very first word, variable. This system, depending upon the size of the system, depending upon the size of the outdoor unit, has up to 168 different speeds. All right, that's a lot of speeds. A lot of you guys may have been exposed to Copeland's digital compressor out in the wild, in Aeon units, some of the larger split systems. We have a couple clients and customers that have digital compressors. Those, they like to claim they have a lot of speeds, but it's a compressor running full max, right? And they bleed hot gas back over into the suction line in time seconds, and that reduces capacity. Those technically aren't different speeds. That compressor runs 100%, and then off. 100% and then off. There's a contactor that pulls in and then it runs full speed. VRF does it differently. They're actually like a VFD drive with a fan motor where they're taking AC voltage, they're converting it to DC voltage, they're taking that DC voltage and charging capacitors like you would in an outdoor unit trying to start a fan motor in a residential system, or a capacitor that's supposed to start a solid state compressor, right? A scroll compressor. It takes that DC voltage that it's charged up in these giant capacitor banks on the boards, and then it trickles it, right? Using pulse width modulation to actually run the compressor at a lower hertz than 60 hertz, and then speed it up, and then speed it down. And it has up to 168 different speeds in that up and down from that inverter board itself. So that's where the variable comes from. And why do you need variable? Why can't we just run it at one speed and then determine who opens and who closes? And it's about efficiency. VRF systems were designed to supply just the right amount of liquid refrigerant or hot gas, depending upon the mode, that is needed. That's it. No less, no more. It's designed to only use the exact amount of electricity needed to meet the demand of the indoor unit or indoor units. VRF, that's the variable part, the refrigerant part, kind of self-explanatory, and the flow part. So the variable, we've got 168 different compressor speeds, which allows us to move a large amount of refrigerant flow to the indoor units, right? Daikin uses volume. Technically, volume and flow, if you want to split hairs, are completely two different things, and they're measured in different ways. But it's all about the same thing. It's about a system, an outdoor unit, whether it's one indoor unit, whether it's 5 indoor units, whether it's 6 indoor units. It's designed to supply a specific amount of refrigerant to those units at any given time. So if we have 3 indoor units, right? 1, 2, 3. And this system is satisfied, this indoor unit's satisfied. We'll say this is, let's say room 101, right? But then room 102 says, I need to go into heating mode, right? I have a heating demand. The person's cranked it up to 80 degrees and it's 70 degrees in the space. They just came home. Unit turns on and it starts to deliver refrigerant to this specific unit, right? It's going to see how far off of set point something is and determine that unit needs a lot of capacity, right? Speed up. Deliver that capacity. And there's a lot of other things that go on between what I'm talking about calling for heating and actually satisfying and delivering that refrigerant. There's other things that take place. But we're not going to dive into a whole lot of that specifically in this class. I'm just here to cover the basic principles of what VRF is, right? You'll notice that we have another indoor unit. And before we get into this particular diagram here, the main premise behind this is just this outdoor unit, its only job is to make sure its customers are happy, right? This one, this one, this one. Depending upon how many you connect to it, its own job, the only job it has is to deliver refrigerant. That's it. And that's all it cares about. It says that you need cooling. It says you need cooling. You're satisfied. You need cooling. Okay, let me see how many that is. Let me see how far off of set point those thermostats are. Let me see how big of a unit it is. These outdoor units know that you're a 1 ton, you're a 6 ton, and you're a 2 ton. No offense to 6 ton. Not saying you're big. I chose those numbers for a reason. But it knows that, right? So it's a smart system. These aren't just systems that are running off of contactors and relays. Yes, some of the older versions of these units do have standard compressors in them, but they also have inverter compressors, and that was just a design phase that we had to work out of our system in our market. But nonetheless, these are smart systems. The outdoor unit is talking to the indoor unit constantly. Somewhere upwards of 200 communications per second between everybody. It knows who's on first, who's on second, who's on third, who needs what. And it uses a PID loop, right, to determine what your needs are going to be. It says you're satisfied, but I see that your temperature has been creeping up by 1 degree every 15 minutes. And so you're eventually going to call here probably in the next 15 minutes. And it predicts that. Now, it can't tell the future. It's going off of data. It's going off of what it can see and how it's operating to determine what it does next, right? But those are all things that are predictive. It's not a magic box full of secrets and mystery. It's going off of logic. And every manufacturer does things a little different, but it's the same premise, guys. It's a compressor or two compressors in an outdoor unit. And guess what? Big shock. The outdoor unit has fan motors. It's air-cooled, right? They make water-cooled VRF, but we're not going to talk about that in this class. It's the same concept. It's using fan motors to pull air across the coil to reject heat, whether that's in cooling, whether that's in heating. Obviously, those premises don't really change that much, but those are the basics. That's it. They're indoor fan coils, as they call them. You call them air handlers. You can call them whatever you want to. Blowers with evaporator coils. I don't care. It's the same thing. It's a fan motor, it's a heat exchanger, and it's some temperature sensors. And that's it. Some units may have a drain pump, but that's it. There's nothing else complicated about it. The whole process behind this is to do exactly what every other split system does. Blow cold air, blow hot air, turn off. Blow cold air, blow hot air, turn off. That's it. That's all these systems are designed to do. There's nothing else crazy complex. There's no desiccant wheels. There's no hot gas reheat. There's none of that crazy stuff that you're going to find in the commercial world when it comes to stuff like this. So, all right, so as you can see on the screen here, right, heat pump, very basic. It's either 100% in heating, or it's in 100% cooling, or it's right in the middle of off. There's nothing else fancy about that. There's two refrigerant pipes, like we're all accustomed to. Standard heat pump. Heat pump is a heat pump. We're not inventing something new. Heat recovery, on the other hand, is a different animal. You'll notice that we've added another refrigerant line. In the VRF world, this is Daikin. There are two different kinds of VRF heat recovery systems. There is a 3-pipe and there is a 2-pipe. Mitsubishi fits into the 2-pipe. They've owned and dominate that market with the 2-pipe heat recovery, with the claims of less copper piping on installation, all these other benefits and features that come with a 2-pipe system. But it is limited, unfortunately. Everyone else uses 3-pipe. There's a few other brands out there that do 2-pipe heat recovery, but Daikin, who else am I thinking of here? Hisense, Hitachi, all these other.
Is LG 2.2 or 2.2?
LG, I believe, is 3.2. Yeah. And I might be mistaken about that. Really, my entire history is usually with Daikin. We've been getting into more lately, but essentially we're doing the same thing. So 3-pipe. You'll notice here on my pretty little animated slide, you've got 3 refrigerant lines. It's nothing new. There's no mystery gas in that third line that no one knows about. It's just hot gas, right? So you've got a dedicated liquid line. You've got a dedicated suction line, and you've got a dedicated hot gas line. On a 3-pipe heat recovery system, when it's in 100% cooling, it's just 2 suction lines. So those 2 lines are always being used. It just depends upon the mode.
So it's essentially a discharge line that's running out there?
That's it.
Yeah.
That's it, yeah. It's just hot gas, dedicated hot gas. And we call it a dual gas line in the world of VRF because it could be either or.
Same like a heat pump, so it's suction line or discharge line.
Correct, yes, yeah. It's hot gas, that's it. So depending upon the mode, it'll determine whether or not it should be dedicated suction, have 2 suction lines, right? More flow, more refrigerant coming back to the outdoor unit, less restrictions, less work on the compressor, or it's dedicated hot gas, sending hot gas to one of these indoor units that's calling for heat, right? Height. This is 2-pipe heat recovery. You'll notice by these beautiful colors, anybody want to take a guess as to what those 2 refrigerant lines leaving my outdoor unit are?
Suction and liquid.
Well, they are suction, not really, no.
One's labeled high pressure gas and one's labeled low pressure.
Yes, high pressure gas, which would be hot gas. 2-pipe heat recovery, it is hot gas and it is low pressure. So as you can see here, right, what happens is the heat recovery box itself is the one that is actually generating the liquid needed for indoor units. There is there's a separator, refrigerant gas separator inside that they call them branch collector boxes or controller boxes, right? BC, everybody calls it something different. In the box, it gets hot gas. It skims hot gas off the top of the line, takes the liquid from the bottom, separates the two, gives the liquid to whatever units are in cooling, takes the hot gas, gives it to the indoor units that are actually calling for heating. And there's a little more that takes place, which we'll dive into in another class.
Out of gravity or out of rejecting?
Mitsubishi owns the technology, and so it's actually, they won't, I mean, you could tear one apart if you wanted to. But they're basically just, when it's coming to the actual box itself, there's a separation that takes place between the actual liquid and hot gas in that line. So, which is why they have specific rules as to why you can't have 90s before the boxes. Otherwise, it creates a turbulent flow, mixes it all up, and you kind of get a slurry.
Right.
It skims that hot gas off the top, takes the liquid from the bottom, and then what happens is it'll actually take some of that hot gas. If it's, let's say one indoor unit's calling for heating, as you see here, and two are calling for cooling. It'll take that hot gas, run it through some actual heat exchangers that are built into the box, and create its own liquid, and then feed that liquid to the indoor units. So even the hot gas that's being delivered to the box can still all be turned to 100% liquid in the process. And so the premise behind this and the pitch behind this as to why this may be a superior system is that there is no chance that liquid refrigerant makes it back down the suction line to the outdoor unit because they have the heat exchangers that are constantly changing hot gas to liquid. So there's that temperature exchange.
You can have two units providing cold and one providing heating, for example.
Correct.
Because one is shooting hot gas.
Correct. Yeah. So the premise behind heat recovery, guys, the secret sauce in heat recovery that makes all of this possible, and it only goes one way, it doesn't go both ways, contrary to popular belief. We take hot gas, we give it to the indoor unit that's calling for heating. What happens when we run hot gas through an indoor heat exchanger with a fan on? What takes place?
Condensing.
Condensing to a what? Liquid. That liquid leaves this box. And instead of going back to the outdoor unit, where does it go? It takes a quick, short little jog to the next unit that's calling for cooling. Energy, heat, taken from this space, is then transferred to this space. That's why it's called heat recovery. We are recovering it from one space, and we are delivering it to another space without having to make another trip around the sun. Instead of going back to the outdoor unit 200 feet away and then back to the indoor unit, it literally just goes here. Now, why do I say it's only one way, right? Because you can't take a vapor and then turn it back to hot gas. You would need a compressor somewhere in here, right? So it only processes one way for heat recovery. It doesn't go the opposite.
It seems like more copper.
What's that? More copper for this?
Yeah.
Well, so it's more copper, it's less work, less energy, right? So if I can run a system at like minimum speed and still deliver enough capacity for 4 rooms, right? By recirculating refrigerant, if you will, between indoor units. It's all about energy, right? Sure, your cost of copper up front, maybe let's say that we'll throw a rough number out there. Let's say it's a 50% increase as opposed to a normal split system. But the energy savings, return on investment on the other side is astronomical, depending upon also the type of use.
So if one air handler is calling in heat mode, gas is getting subcooled, condensed to a liquid, where's that liquid going?
It's going to come back over here on the common liquid line, and it's going to come up over here back to this indoor unit.
What if that unit is not calling?
Then it'll go back to the outdoor unit. Yeah, so we're gonna get to that, but it's a good question. So every manufacturer is different, right? So Samsung's short relationship with Trane resulted in solenoid valves in the branch selector boxes. They only change. It's like a 4-way valve, guys. It's determining which way traffic's going. Are we going this way? Is hot gas going this way, or am I going to just do suction and liquid, right? The metering devices for these systems are always in the indoor unit. There is always going to be an electronic expansion valve metering flow at the indoor unit.
It could also act as a solenoid too, though, right?
Well, sure, it could close, right, and it could open. Other manufacturers like Daikin, they don't use solenoid valves. They use electronic expansion valves. And those are usually 0 to 3,000 pulses or 0 to 6,000 pulses. And so they're like fancy solenoid valves because they soft open and they soft close. Everybody has seen a house or been in a house where you shut the water off quickly and the pipes hammer in the wall. The same concept is true in chilled water. The same concept is true in refrigerant, right? If something is moving at a high rate of speed through something and you close it quickly, it can create noise. It can also create turbulence, vibration, nuisance calls. So some manufacturers use electronic expansion valves because it's a slow close and then it's a slow open. And then they just have timers in between to slow the system down or like a wait period, if you will, like a hot start. So, and then you'll see 3-pipe here, right? Low pressure, hot gas, liquid. All right, let's talk about sizes. Heat recovery comes in a bunch of different flavors, and so does heat pump. VRF is just all over the place. And now this is just commercial VRF. There is residential VRF. I have a 5-ton VRV system on my house with 5 indoor units. I am not fancy. I just like to shop off the discounted list from the manufacturer of discontinued products. There is something for everyone. So the premise behind VRF, the one side, energy efficiency. The other side, flexibility. You can literally fit one of these products anywhere to meet any need. As you can see, we have one in every voltage, including to accommodate, some people on the California coast and in Canada of the 575 voltage, which you'll probably never see here in the state of Florida, which is that lower side. But we have it all the way up to 40 tons, right? So I can take 2 VRF condensers and put them side by side to replace 40 tons worth of capacity on a split system. And as you see, as we go up in tonnage, the cabinet sizes get bigger, you have more outdoor units, they'll all be tied together, they all work together. In a series of 3 outdoor units, one is going to be in charge, the other ones are going to follow that one's orders. That's how all VRF systems are. Doesn't matter the brand, doesn't matter the manufacturer, someone has to be in charge. This is the systems that we'll be installing shortly on a project. This is their latest and greatest series from Daikin. This is called the Emirion series. It's been around for 2 years now. We finally got our heat pump version from the manufacturer imported in. You'll see we have 4 different sizes. 6-ton, 8 to 10 ton, 12 to 14 ton, 16 to 20. And I say 4 different sizes. They're actually sizes inside of the sizes themselves. The cabinets don't change. It's just a matter of compressor speeds and fan speeds, right? So you'll find that the 8 to 10 ton cabinet looks just like the 12 to 14 ton, but you'll notice it has one bigger compressor. You see that on the side there? And you say, well, how is that possible? How do we have an 8-ton unit and make it produce 14 tons of capacity? It's the variable part, right? Certain models like the 8-ton would limit its compressor speed top envelope, so it can't go over a specific speed. You'll find the higher the tonnage, it has actually higher fan speeds, it has higher compressor revolutions, sometimes it has a larger compressor, so they're just moving more refrigerant, moving more airflow across that actual outdoor heat exchanger to deliver that 14 tons of capacity.
So they're the same compressors in those?
There are 3 types of compressors. There is the 57, as you see on that first one under the 6-ton. There is the 35, and then there is the 57, which is actually vapor injected. And so as we get into the realm, which is on the far end of that vapor injection side, that's when we get into the fun realm of compression ratio. Brian had a talk with you guys recently about compression ratio, right? Vapor injection just helps bring that down in low ambience and high ambience and whatever scenarios that you might find yourself in. So we will dive into that. But it does exist, right? So VRF, VRV, you'll find that a lot of these larger tonnage systems have vapor injection on the compressor itself, which is nothing crazy. And we'll talk about in a service troubleshooting class that I have. Man, does that look intimidating or what? I can tell you the first time I saw a VRV system, it kicked my butt. It kicked my butt for 3 days. 3 days. You pull the cabinet off and you're just like, there's no way that I'm going to figure this out, right? I don't even know what any of this stuff does. This is just made up, right? There's no reason they need this many copper pipes going in this many directions. This is the smaller chassis. This is the medium chassis. This is the big boy chassis. This is the system that we'll be installing here shortly, the 20-ton. We're actually doing 2 of them. It's going to be a lot of fun. You'll notice that something that these systems all have in common with each other is that there is a nice, beautiful little refrigerant loop right there. When we take AC voltage and we convert it to DC voltage and then we trickle it through pulse width modulation to our compressors and our fan motors, because they're both DC voltage driven, they're both pulse width modulation, they both have a bunch of different speeds. It generates what? Anybody? Heat. It generates heat. Back in the day, they used to be air-cooled inverter boards. They used to go to a heat sink, and then air would come across them, but then they found it was a very archaic way to do things because these heat exchangers inside the outdoor unit, when it's 110 degrees in Arizona, and you're in cooling, and you're moving that 110-degree air from the actual outdoor heat exchanger across these fins, it just overheats the inverter boards, and they die prematurely because of overheat. So they changed it to actual using liquid refrigerant to cool the boards. And you say, oh my gosh, inverter cooling using refrigerant, that's genius, but how do you keep the boards from sweating? Anybody have an idea? How would you keep the boards from sweating? Air, sure, but then why not just make it air-cooled in the first place?
You just said why not.
Exactly. We use liquid refrigerant. You take liquid refrigerant. So let's think about this concept, right? Does anybody know what the average temperature of an engine in your vehicle should run at? Around 180, 200 degrees, depending on the model, right? Anything below that, compression's not great, right? You get a lot of problems, you get a lot of issues. Above that, it's too hot, right? Can't function. There is a sweet spot with inverter boards. We don't need to keep these in sub-zero temperatures of 0 degrees, right?
The liquid temperature is not that cold, so it's not going to.
And it's a liquid. It's not going to change states.
Right.
You can add heat back to liquid.
Yeah.
So all of these pieces of machinery, that bottom channel in the actual outdoor unit is constantly in a cooling mode state. That means there's hot gas going through the bottom channel, regardless of what mode it's in, generating liquid only for the inverter boards in the actual outdoor unit. You take a 90-degree liquid and you run it across some heat sinks of 2 fan inverter boards and 2 inverter boards for compressors, and you pick up, an extra 30, 40 degrees of heat, and then that liquid then just gets dumped right back into the liquid line itself. Right? Such a small quantity compared to the entire system itself that it's unnoticeable. So if you ever see that running across the board, you'll see it in residential units. The Daikin Fit product that we have, that we've installed a few of. Not even that. There's going to find Trane uses it, Lennox uses it. Everybody's gone to liquid cooled inverter boards, right? And the name cooling, everybody assumes, okay, it's cold. It's not cold. It's just less hot, right? All these terms that we use in refrigeration and in HVAC, they just need context. Indoor units. These are all of the ducted units. As you can see, there's a 100% air processing unit, there's an energy recovery unit, there's a gas furnace, there's a multi-positional fan coil. Multi-positional is just the regular air handler that we all know and love with an aluminum coil, right? We have a high static ducted unit. It's like a pancake. Everybody's heard the term pancake unit, I'm sure. It's been around for a while. I'm sure we've seen some mini splits like that, right? They have a high, medium, low static unit, right? We don't ever install the low static because it's completely useless. Everybody gets the low static unit because of cost, and then they put like 40 feet of ductwork on it, and it literally just grows mold because it can't perform. These are all the ducted units. As you can see, they're slim for a reason, guys, for flexibility. You can put it in a drop ceiling with only 7 inches of clearance, some models. 12 inches of clearance is all you need. You can get a 3-ton unit in there. You can get a 4-ton unit in there.
Doesn't that make them completely unserviceable?
Yeah.
It's a good point. It's a very good point. So I'm glad you brought that up. Almost every single VRF unit, mini split, I don't care who makes it, if it looks like these bottom 4 units there, they're serviceable from below. That means drain pan, sensors, expansion valves, whatever it may have, fan motors, they're all serviceable from below. So if you are installing one of these, if you are servicing one of these and you come across it and you have to open it up because you think something's wrong or it's making a heck of a racket, right? And you got to take it apart, and they mount it right on top of the ceiling of a hard lid, or they put nice little, and they love to do this, engineers. They put that secondary drain pan with the rails, and they sit it on top of that, and then they hang it from the ceiling with chains for the pan, like a normal air handler. Because they don't know any better. You literally have to rip the unit out and rehang it just to get to all the components inside, because they're not serviceable from the side. Now, sure, the boards you can get to from the side flared connections for refrigerant lines, drain line, everything's from the side, high voltage, all from the side.
Right.
But all the other major components for serviceability, it's from below, which is why it is so important to read the installation manual and see what the actual required service clearances are. You'll find that the service clearance for underneath a unit like that, sure, it fits and it's a great design, but I don't think a homeowner is going to be okay with a 48-inch by 30-inch access panel underneath a unit in the middle of their living room. It's just hideous, right? It doesn't make any sense. Indoor flexibility, right? This is ductless. A lot of products. You'll find some of the manufacturers who are very late to this game, VRF, they have very limited product lineup, right? They have 2 units, they have 3 units. Daikin has somewhere close to 16. They're working on 18 here shortly, including hydronic floor heating for water. You've got your wall mount. Everybody knows that one, right? Everybody's seen a mini split on a wall. There is a VRF unit, right? It's actually probably the most common one that's been sold the most in our market. 2x2 cassette, the 2x2, 2 foot by 2 foot, right? 3 foot by 3 foot cassette goes all the way up to like 4 tons. Ceiling suspended, you'll find that one in the classroom. One-way blow, that is basically just a fancy cassette that goes on the edge of a room instead of in the middle of the room. Return air opens up from the backside, blows air across the room. It's actually got a really strong fan motor in that one. Exposed floor standing, right? You'll find those in northern climates, you know, where they have mostly heating. Sucks in air from the bottom, blows it out of the top. Then you've got concealed floor standing, which can actually be built into a cabinet assembly like this. You can stick a VRF unit in here, put a supply grill on the top, put a return grill on the bottom left-hand side where no one sees on the end of the cabinet, sucks air down through the cabinet, blows it out the top. And then the under ceiling 4-way cassette. So listen, there's so many different types of units that you can literally find a unit for any kind of application, for any kind of customer. Let's talk about capacity sizes. Do they really make it all the way down to 0.4 tons? Yes, they do. All the way up to 8 tons. This is the wide range and flexibility of VRF. I can go to a project that has a 20-ton system and still put a half-ton mini split in a closet or a small office and still hit all the other needs of the building itself. And only cool or heat that space when it's needed. Not just dumping air all the time whenever I have to, or zoning it. Nomenclature, right? I don't expect you guys to know this. Just go in this actual manual itself and you'll be able to read what the model numbers are. The biggest one that I'm going to point out here that you need to know is capacity, right? You need to know exactly what type of capacity that unit has. And you can tell that by the 2 numbers that are in the model number, right? So if it's an FX MQ, the M stands for high static, Q because it's R410A, which might change here shortly in the next couple of years. If it's an FXMQ36, what does that mean? It's 3 ton, 36,000 BTUs, 12,000 BTUs per ton.
They're normally going to be divisible by 12. Like that.
Always. Right. And then you'll notice the VJ at the end. All the indoor units are 230 single phase, 230, 208 single phase. It's the outdoor units where you get into the weird voltages of 460 or that's all the letters. They all mean something, right? All right, so let's talk about a heat pump. Can anybody tell me what these are, why they matter?
Splitters? Reducers?
Yeah, they're splitters. Takes 1 to 2. Hopefully this isn't a new concept to most of you guys. We do it in high voltage all the time.
It seems like we should use those instead of T's.
Yes. And there's a big reason for that, right? Every manufacturer uses a different type of, I'll use your term, splitter. This is what it is, right? When you take something from 1 and you take it to 2, you're essentially splitting it, right? Cutting it in half, redirecting it. VRF uses 1 line set for the entire system. That's it. 1 line set.
What are these actually called?
This is made by Daikin. This is called a Refnet. And the reason that is just because they did a bunch of scientific testing. Obviously, they invented the technology, and they've changed it only a very short amount of time to a different type. But the way that it's set up, right, you've got, this is going to be a suction, right, or hot gas, and this is your liquid. The design premise behind it is that where it actually splits creates the least amount of turbulent flow and allows an equal distribution based upon which one might be calling. You'll notice that they look a little different, right? They're a little shorter on one side than the other. Anybody want to take a guess why that is?
Equal volume.
Yeah. You'll notice that this one on my left-hand side, right, is the one that continues on my main line set.
It's going to be the path of least resistance.
Yeah, because I've got other boxes to supply. I've got other fan coils to supply. I'm trying to create a common channel. This is the one that would then branch off and go to my indoor unit or go to my branch selector box. That's the difference in these two. You'll also notice that there's beveled edges here. You can pass that one around that way. Anybody want to tell me what those are for?
Create a restriction.
No, close. You're thinking.
Reduce turbulence.
Maybe.
Definitely reduce turbulence because of the U shape instead of the T that kicks the pretty.
Well, yeah, the T is awful. And at one point, Daikin used T's on their outdoor units, connecting them together, and it just creates a ton of turbulence. It creates a ton of restriction. It just literally, is like throwing a water balloon at a wall. It just goes everywhere, right, in the refrigerant line. We're trying to create less resistance. When you have literally a half-ton all the way to an 8-ton system, you have to have the ability to connect anything to the system. Those are actually reducers and couplings for different size refrigerant lines. So based upon the type of indoor unit and its liquid line size will determine, do I cut it? Do I leave it at the 1/4-inch connection at the tip? Or do I cut it one notch back where it expands to 3/8? Less braze points, less leaks, less contamination, less time. That's a small indoor Refnet kit. You'll notice that every Refnet kit has a specific model number with a specific number in that model number to tell you what size piping it's rated for. You'll pull out the installation manual of that and it'll tell you. It even comes with little actual copper reducer pieces to upsize it, to downsize it. It's all designed to ensure that no matter where in the system this fan coil lands, let's say it's a 3-ton at the very end, that the piping has been sized correctly to ensure that at a full demand load on that unit, that I can still deliver 100% capacity at any given time, and that I'm not restricted. Why does that matter when we talk about those? So you'll notice how they're laid out on the table right now. Let me ask you this question. Does anybody know which way these should be installed? This way, this way, this way. What do you think is going to be the most?
I'd probably say horizontal. Yeah, that way.
Why is that?
Just to keep the path.
Path of least resistance, right? To keep it equal. You change this, right? Gravity's different. I mean, it may be a small amount up, right? But when we install these, when we see these in the field, they're supposed to be plus or minus 15 degrees off of level. Slight deviation isn't going to kill it. But when you see installations like this, what happens is, right?
All the liquid goes to the bottom.
What happens? You start to pull oil. So let's say this is on a closet that has no heat load or cooling load at all, and that unit barely ever turns on. During normal operation, when you've got refrigerant flowing back, right, you're going to get oil that's going to trap in that line. Everything is intentional. That's the premise behind VRF2, right? So yes, we have all these indoor units. We have all this flexibility. We can do all these things with VRF. But something so simple as this to this can kill compressors, can cripple a system, can deliver awful capacity to the fan coil that's connected to this one, if I put it like this.
Is that a common issue?
Yeah. Well, you get guys that come in, and no offense to manufacturer training, but they're too long. It's 3 days. You get technicians who have come in from working out of town at night, and they came in for the donuts and the coffee and the sandwiches, and they go through 3 days of being told, don't do this, don't do this, do this, don't do that, do this, and this many inches, and that size, and this and that. And so they just get hit over the head with so much information in such a long, drawn-out period. When they leave, they don't even know what they learned in the first place. When they go to the job that they were trained for and certified for, a year later, they don't remember that. They've got a deadline to meet. They've got a boss breathing down their neck, right? They just want to get this done. But yes, that is a common thing that you find. So that's the thing, right? VRF is complex. To me, it's a beautiful piece of machinery. To others, it's a very large source of frustration. I would say probably 96% of all failures and problems with these systems is installation related. It's because no one stopped to tell you how important this is, right? And the science behind it. And so this is a heat pump system, right? Very basic. You can see there we split off. We go to our indoor units. They've got controllers. This is a heat recovery system, right? Essentially the same thing. Those are not T's, just so you know. They just don't have the picture of the Refnet on there. They go to a box. There's a bunch of different ways to set this up, as you can see here, right? We've got a 1-to-1 configuration on that first fan coil, where it's just one branch selector box to one fan coil. That fan coil can do whatever the heck it wants to. It can heat, it can cool, it can run in fan mode. But then you'll notice that I have one branch selector box connected to 2 fan coils. Well, now these 2 fan coils, they are coupled together. They're married together. They have to make decisions together. They can't just do one thing and the other one does the other. They're both tied to one box that's going to determine whether it's heating or cooling. And there'll be a master and a sub controller. One of these controllers will say master control, which means that it is not in command. It's very misleading, right? The controller that has nothing on it is the one that's in charge. Don't ask me why we do things the way they do.
Where does it say that on there? Is it visually on the screen?
On the top, yeah. But that's it. So, you got one unit, 1-to-1, right? Does whatever it wants to. Then you got the 2 units that are on one box. It's married to another. So if you go to a service call, you look at a system, and you can't make changes, it only goes into cooling, it won't go into heating, you have to look for the other unit that might be on the same system. It might be a giant apartment, and there's 2 units, and there's a controller somewhere else in the back bedroom. All right, there's other rules that we've talked about. That turbulence. So when you have a large system like this that's operating the way that it does, something that comes to my mind frequently, and that's only because I've been troubleshooting it for so long, when you have one indoor unit and one outdoor unit on a split system, and the refrigerant is doing this, right? What's one thing we don't usually typically worry about?
Explosions.
Well, yeah. Give it a couple years. Oil. When I've got a split system, like the one behind you there, and my outdoor unit is only 50 feet away, and it's just a standard loop. It's either going this way or it's going this way as a heat pump. That's one thing I don't worry about. Oil. It's a short distance. It's only doing this in a small revolution. Where's it going to go? But when I take this, and I go, oh yeah, that looks nice there, and then you know what, let's do this over here. Yeah, and then you know what, while I'm over here, let me just go back over here real quick, and I do that. This is your typical VRF system. You're going to find a lot of engineers that don't know how to design a system correctly. I can contest that. I've been to a lot of job sites all over the U.S. looking at systems like this. Do you think I have to worry about oil on this one? Yeah, I do. Oil management. Okay, so why are we talking about oil management when we're looking at a slide about clearances? That comes back to turbulence. When I've got refrigerant moving in a straight line, it's happy, right? Not a care in the world, driving down the coast, hair in the wind, right? Top down. When I hit a 90-degree elbow, it's like a car crash. And it changes direction, right? What do you think happens if I put this at the end of a 90, right? If I 90 it over like that. Let's say, it happens right here, right? There's a 90. Well, let's change our direction.
You're going to be turbulent going into that.
Yeah.
Crazy turbulent.
Yeah.
It's going to be noisy in heating. Vibrations. I'm thinking about the oil, because that's usually what it's all about. You're going to get oil trapped in specific fan coils. You're going to get capacity losses. It's going to literally sling it everywhere. It's going to go every which way. And you'll find that if that happens and it's horizontal like this, and then it goes down to it goes down to a unit that's below other units in general, that fan coil, when it's off, is going to pool oil in it. And Lord forbid it's a room that they don't ever use anymore. It never comes on. You get 50% of your system's oil trapped in a line to an indoor unit because these weren't followed. Everybody says there's suggestions. There's suggestions. You know what? You don't want to do it? I don't care. That's cool.
Like stop sign.
Yeah, like stop signs. Exactly. As long as nobody's watching, did you really stop? I mean, do you need to? This matters. This matters because of this. Because of oil. Compressors come pre-charged with a certain amount of oil. It's still their responsibility, their job. They have parameters. They have safety features that are designed to run the system in a specific way to get that oil back to the outdoor unit. But listen, it can't do everything. It can't overcome physics. It can't overcome gravity. The rules and laws of physics still apply to this particular system. It doesn't live in a separate dimension doing whatever it wants to. So when you break these rules, when you go less than 20 inches, right? And so there's certain applications where, sure, I could not avoid it. Okay, just don't do it again. Keep an eye on the system, watch it. But when you consistently go out of your way and you do an entire system like this, just go ahead and order the compressors, right? Keep them in your warehouse. That's it, yeah. Put it on your calendar, 1 year from now. I should probably go change that compressor. And then there's that angle degree that we talked about before, right? Not up and down. They changed it from 15 degrees back when I took this class 11, 12 years ago, maybe even 13 years ago now. And they do plus or minus 30%. It just can't be like this, guys, or this. Common knowledge. This is a typical layout. Looks like fun, doesn't it? This is the 5 o'clock emergency service call on a Friday, right? Yeah. Finding out which unit it is, which one has the issue, right? You pop the ceiling tile and you see this and you're like, I just want to go home. Just want to go home. So this is your typical VRF system, you know, whether it's multifamily, whether it's, you know, whatever have you. They have boxes that will actually support up to 12 indoor units on one box, right, for one specific zone. Some manufacturers have 18. You know, imagine cross-wiring and piping on that. It's a lot of fun.
Those boxes, all 18 units on one box, can either run heat or cool at the same time.
Mm-hmm. Any given time.
Yeah.
Now, there are certain limitations with anything else. Most manufacturers have an outdoor ambient lockout, so if it's above 75 degrees, it won't let a box go into heating. It won't let an indoor unit go into heating. The unit is smart enough to look at outside and say, really? You want heat? Come on. No, I'm not doing that. That's stupid.
What causes the limit?
The limit, ambient.
No, 12 to 18.
So, and that's the wild thing too, the 12 to 18. You're talking about the capacity limitations on the box itself. It's usually actually double what you find on a normal box. And so, like, you know, if you get a box with 12 indoor units or, you know, 18, let's say 18 indoor units and they're all 1 tons, that's 18 tons of cooling capacity. It can actually handle more than that. It can usually handle up to like 24 tons.
The limit's really the boxes adding up to the full capacity.
Yeah, because you can also take these boxes here and instead of connecting, that's the thing, instead of connecting 18 indoor units on 18 ports, I could probably connect up to 24. Because I could take the one line off and I could branch it to 2 indoor units and they're both tied to that one port. So I mean, they both have to do the same thing at the same time, but I can still deliver that same capacity. It's just flexibility. And all of that also comes down to refrigerant piping size, being able to give that capacity to get that flow through there and the volume that you need to those units. And there's not a whole lot of restrictions in these boxes, the way that they're set up. So, but that's the thing, right? That's the premise behind this. Instead of having 15 outdoor units on the roof for 15 split systems inside, it's a nice, pretty little package on one stand and then 15 indoor units inside.
And it's more efficient.
More efficient. Well, and the reason this gets a bad rap is because they get installed very poorly by the cheapest bidder and they get a bunch of failures. And then you get contractors who don't know how to service them or work on them, and then it becomes, you know, a perpetual nightmare of just cost and cost and cost. So this is your, so bunch of different types, right? So VRV, VRF, you're gonna find a bunch of different models. Some look like spaceships, some look like this on your screen, right? This is a VRV X. This is their last series of equipment. We went from X to a Mirion. The Mirion's the one that I showed you. I'll show you at the end of the presentation here what it looks like. The VRF comes in all different shapes and sizes, so if it looks kind of like this, it's most likely a VRF unit. You'll notice there's a service window up there in the top left-hand side. Older models don't have that. You actually have to pull the whole panel to get to it. You know, even older than that, it's still the same thing. Something to remember with these units, all these units typically come with brackets under the compressors from shipping, right? So when we think about an inverter compressor that has 168 different speeds, We think about what? When something is moving extremely fast, what does it do? Vibrates, creates vibrations. Very, very fast micro vibrations, right? Well, when you take that, whatever that may be, and you bolt it down to where it can't move, what happens? It causes damage. It can't do what it's supposed to do. It can't move the way it's supposed to. So all these units come with shipping brackets to make sure the compressors don't clang around inside. You have to make sure you remove the shipping brackets under the compressor. If you go to a VRF system and it's got a failed compressor, or the compressor is making a gosh awful racket, or you put your hand, everybody's done it, you put your hand on the unit, you're like, ugh. Look under the compressor. You might find a shipping bracket underneath the compressor. If I had a nickel for every time I found a dead compressor that had been shaken to death over a year, some make it a couple months, some make it 2 years, where these are still underneath there. They make them yellow, but the blankets cover them perfectly. So if you're the one that's installing a unit, just check it. Yeah, this is your BS boxes, right? Single port, multi-port. The reason I threw this in here, look at all these lines, right? On the outdoor unit, do you see anything in there that's got like giant signs or blinking lights that tell you what's what? No, it doesn't. As an installer, it would be very easy to confuse what lines go where, and it happens actually a lot more than you think. Know your product. Look in the installation manual. Look for a label, because you'll notice on the single port BS box, on the 3 lines that come to the box, right? 3 lines from the outdoor units to the BS box, you'll notice they've got lines mixed up. They did that just to hurt your feelings and make problems, right? Look at that compared to the multi-port. You'll notice that the high-low pressure gas is no longer in the middle, it's on the bottom side. Don't assume that that line is what it is. Read the label on the box. If the box doesn't have a label, look in the manual to ensure that they are connected to the correct lines. I've seen gas lines hooked to liquid. I've seen liquid lines hooked to hot gas lines. Oh, the data is wild on how the system operates. Understand your system. Oh man, this is a long topic. We're going to simplify it. Traps, just don't do them. This isn't the 1950s. We're not dealing with R22 anymore. This isn't POE oil. This is PVE, polyvinyl ether. It doesn't require the same trapping rules that you would normally find on risers or distances. The system has the ability to overcome that height distance as long as you're within the design parameters, which I'll show you. There's a program where we put all these numbers in and it says, no, you can't do it, or yes, you can do it. You don't have to be a rocket scientist or understand the extreme complexities of these systems. You just have to know how to measure pipe with a tape measure. That's it. Well, and write it down. That's also the other part that everybody forgets. You don't need traps. Avoid traps. And the reason we talk about avoiding traps is that beautiful picture that I drew you earlier about turbulence and oil. Traps were put in back in the day on split systems with vertical risers to what? Help push that oil back up to the outdoor unit, right? Or to keep oil from trapping inside the indoor unit and making it back to the outdoor unit if it was higher. It's not needed on VRF. And that's because we have oil return modes on these systems where the system will actually open its expansion valves, turn its fans off, and flush a large amount of liquid through all of its indoor units to bring all oil back at any given time. It does that automatically. And the calculation behind that is it takes compressor revolution speeds. It takes the knowledge and understanding in the programming that at each speed, how much oil is lost at that speed. It does a total calculation to find out exactly how much oil has been lost to say, oh, my compressor should be low on oil, go into oil return mode. It knows what it's doing. But when you add traps to the system, guess what? Now it doesn't get that oil back like it's supposed to. And so when it's doing that calculation, it thinks oil levels are here when oil levels are actually here. And so as it gets lower in the calculation, then you run unlubricated, 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 and then it goes into oil return mode, and the damage is already done. And you do that, rinse and repeat 10 times a day, and that's how you lose compressors. Traps are what kill compressors, and that's because of oil. The more complex the system, the longer the runs, the more detrimental something like this is. So that's traps on the main line. You notice the second picture down below is not traps on the main line. This is actually after a Refnet. So when you leave a Refnet, you actually have that 3.3 foot variation. So you can go up and down, spell your name in the ceiling, because you like to leave a mark, you like to make a statement. I don't judge. Right? And then it goes to the fan coil. that's not an issue. It can overcome that because there's refrigerant that's going to be flowing through that. But when you do it on the main line itself that supplies all the other indoor units, the amount of oil that's being commuted down that line to the outdoor unit is in a larger quantity. It causes more issues. Outdoor unit, airflow, discharge, stuff you probably don't even need to know. Discharge at a 30-degree angle. Why is that important? You don't want to put a unit right up against a wall with an overhang. You're going to find that the hot air that gets discharged out gets recirculated back around, reduces capacity, causes service issues. It's that one call that you always get a high-pressure trip on in the middle of summer, right? It's just not a good idea. Use your brain. Outdoor unit placement, that's that we talked about before, right? Just be mindful of that 30-degree discharge. We want to have enough room to where I actually can get rid of the hot air coming out of the unit or the cold air coming out of the unit, that we don't get that recirculation. You'll find in the installation manual what those minimum distances are. You're actually allowed to put the units up to 3/4 inches away from each other, side by side. It's the front, back, and other sides that become the issue of where the air is going to be coming in. So you can stack them 3 all together, sandwiched together with a 3/4 inch clearance. But when you do that, you have to make sure you maintain that 3 foot, 4 foot, 6 foot on the outside. Flaring, this is a good one. So we're going to actually have a class on flaring. Not now, obviously. I'm still waiting. I bought a bunch of stuff. Oh, you just wait. Why does flaring matter? Why is flaring important? Does anyone know what this is on the screen here? On the bottom, what is that? Bottom right-hand side? Flare gauge.
Copper needs to be thick enough or strong enough to hold though.
When we get into VRF, we have that third line, right? Which usually isn't flared on, it's usually brazed on, but you have that third line that can go from hot to cold in a matter of 5 minutes. We can go from a 45-degree suction line to a 165-degree discharge line. 5 minutes. What happens when things go from cold to hot?
Weakens.
Expands. What happens when you have metal on metal pressed together that's constantly expanding and contrasting? Right? Shifting, cracking, breaking, leaking, right? You will find that most of these installations on VRF, no one has no idea what that flare block is, that flare gauge, or they've never used it, or they've never seen it. I was that guy for 3 years.
Are they flared into the boxes or is
There are some manufacturers that do flares at boxes. All indoor units for VRF are flared connections except for the vertical fan coil, which is brazed. So you can't get away from it. Okay. You have to flare every single indoor unit. So flaring is important. So you're going to find when you go to leak check a VRF system, right? Typically you want to start at the indoor units, work your way to the outside. That's just because Joe Schmo, took that 100-foot roll that he had and he spooled above the ceiling and he never actually redid the flares on the mechanical press fittings that come from the factory. Don't worry, I've done it a million times, so no judgment here. But you can see on that X line how short that flare is. That surface area is extremely small, as opposed to the actual correct flare, which is on the top side. If you used a flaring gauge, it would have passed right through, and you would have told you it's not the right size. The top one has an increased surface area, which is actually designed to make sure that is a sound seal. Because these systems can operate upwards of anywhere to 600 psi, right? All the way down as low as 15 psi. It all depends on the mode, the climate, where you're at, what it's doing, charge. You'll find incorrect flares. They will drip oil.
Yeah.
They'll leak a little bit of refrigerant, not enough to damage capacity, but you'll see it. Ceiling tile, oil stain. Gives it away every time. You go to grab that line, and it just oozes oil. That's because the flare is too short.
That gauge, is that measuring the pipe size or the actual flare size?
So it says that if you have a 1/2-inch pipe, when I make a flare, when I flare that 1/2-inch pipe, it should fit into the 1/2-inch gauge at the end.
So it's after you make the flare.
It should fit in, but not pass through.
Okay.
When we have the flaring class, I'm going to show you. I bought a bunch of gauges for everybody. I bought a bunch of flaring tools for everybody. We're going to go through it. It's called a no-go-go gauge. So there's actually it's a hair bevel inside. It is. When you see it, you're going to be like, there's no way. If it fits in the gauge, it doesn't pass through, it's the perfect size. If it passes through, it's too small. If it doesn't fit in the gauge, it's too big. And then torque, we're going to also get into that too, about a bunch of torque wrenches. Listen, guys, I know that it's difficult to have all these customized special tools or to do it every time, but I'm going to make it easy to do the right thing, right? That's the whole premise that we have here. We're going to make it easy to do the right thing and very difficult to do the wrong thing. So the other side of the flares being correct is also the tightness. I can guarantee that your torque on a flare nut and his torque on a flare nut are wildly different.
Sure. Not if there's torque wrench.
Not if you have a torque wrench. Because the torque is exactly the same on every single flare. And why does that matter? Because we get into that system that has 200 pounds. And it's an assisted living facility. And all the copper is ran in hard ceilings. And to access the indoor units is a nightmare.
How do you feel about the people that say your torque rating changes based off if you use nylog or not?
Well, so it's a good point. The same thing comes when you lubricate the flare itself. A good proper flare that is done using a flaring gauge, deburring with all the right practices, will never need nylog. It will never need oil. It doesn't need to be lubricated. We've been using flares for, plumbing, anything, for many, many years, right? These two metals together, when they're clean and done properly, don't require any kind of sealant. Sure, you can nylog it if you want to, right? You can go through.
They're pretty easy as long as you pay attention and you follow through with what you're doing.
Yep. So yes, so if you get nylog and you put nylog on it, you put a lubricant on it, then sure, yeah, you could actually slip it farther than it's supposed to go with a torque wrench. Maybe not that much farther, but a proper flare doesn't require any kind of other sealing material. It doesn't require thread lock or thread sealant. It doesn't require, and you'll find the bad mechanical contractors is when you go to the inside unit and you find that it's covered in pipe dope.
How about vibration?
Vibration for what?
You shouldn't have vibration.
Fan motors are isolated on rubber grommets. It's a DC-driven fan motor. The unit is balanced for efficiency, and when it's hung, it's even on rubber grommets itself. And so there should be no vibration from the indoor unit or any vibrations, micro vibrations on the actual hanging rod or the pipe itself to cause any kind of issues with the actual. Yes. If your pipe is supported correctly, you won't have any extra additional weight on there. So what happens when we've had a whole class on this. We've had a whole series on this. What happens when we braze without nitrogen? Oxidation, cupric oxide. Yeah, we don't have to.
Nothing. You should do it all the time.
All right, somebody mute him and kick him off this call. Okay, oxidation, sure, yes, it's going to get stuck in the system. It's going to cause all this kind of damage, but why does it also matter on VRF? We have electronic expansion valve. This is the needle inside of electronic expansion valve. As you can see on the left-hand side on our clean system, it is extremely polished, it's clean, right? That seats right down here in perfect seal, no refrigerant leak by. When you get dirty, nasty, grimy materials in there that scar, that copper flowing through the system, because there are no filter dryers on VRF systems, right? They're just metal strainers, and they don't catch a whole lot. It will actually scar the end of that needle to where when it goes to seat, it doesn't seat all the way. And you get refrigerant leak by. And now you've got liquid refrigerant dumping into a fan that's off, that then makes it back to the suction line, that then makes it back to the outdoor unit. You multiply that by so many units, and then now your outdoor compressor is chugging liquid. Scrubs all the oil out of the compressor. Compressor still thinks it's got this much oil when really it's got this much oil. And that's what happens. That's the story that's on repeat all over the U.S. that kills this equipment, that gives it a bad name. That's an installation deficiency. Hi, then you'll see here VRV Web Express on the right-hand side of the screen. This is the report that's generated, right? So I go out and I say, hey, based upon the drawings, this is what it should look like. You go and install it. And it's 10 feet different in a bunch of different areas. It is your job as the installer to document those changes, or not even document the changes, just measure your lines. Go off this report, cross it out, 10 feet here instead, 4 feet here instead, 5 feet here instead. And that gets put back into the report because the total charge added to this system isn't based upon superheat and subcool. It's based upon liquid line length and size. So you can't properly charge a system unless you know without no doubt in your mind that the liquid line is that exact distance and length. So measuring is extremely important. But that's how critical it is, guys. So we talked about the Refnet installation. We talk about traps in the system. But it all comes down to this beautiful tape measure here, right? Using it, ensuring that it's accurate. And I don't want to come back and find that you've got, 15 feet, 0.8777 inches on this line. Sure, go for it. I don't care, right? But I can tell you that I've looked at a lot of these reports over the years, and when it's a round even number, I call BS. And sometimes we have to do a guess on that, right? And so yes, 1 inch here, 2 inches there, sure, not going to be killer. Now, 5 feet here times 10, that's a lot of refrigerant charge. And so it can go either way, actually. And that's the issue, right? It can go either way. If I'm 10 feet off in 15 different places, that's 150 feet. Let's say it's 150 feet too much, right? Let's say that I only have 100 feet of piping, but I accidentally calculated an extra 150. Now the system's overcharged, right? And you have issues with oil getting back to the outdoor unit because the compressor can never ramp up because it's going on high pressure step down. Let's say it's 50 feet too short because I look at it and I go, yeah, that's 5 feet, and it's really 50 feet, you know, and I pencil whip it. And now the system is 15 pounds undercharged. And now the compressor is constantly dipping down in low suction pressure. And now it's on low pressure step down. And it can't meet capacity because it says, I'm hitting my target. I'm sorry that you don't have enough liquid refrigerant. I'm still doing what I'm supposed to do. They're smart systems to a point. They still are very dependent upon the installation, which is something that Kalos does extremely well. We're very thorough. We have a great attention to detail. We have great staff here. You guys are here for a reason because you're good at what you do. You enjoy what you do, right? It's my job to express to you how important this is. So the reason the measurement of the lines are so important is, one, it's refrigerant charge, but two, your distances determine the diameter of the pipe. If I've got a 3-ton unit that's 25 feet away and I've got a 3-ton unit that's 350 feet away, I have to account for those restrictions. That's a long way to go. It's additional friction in the pipe itself. And so my system, my computer program tells me to take that liquid line from 3/8 and make it 1/2 inch. But if I never calculated that and never wrote it down in installation, I would have never known that that liquid line is undersized. And I ran it in 3/8 anyways, because that's what the program says, right? The program doesn't know that it's actually 350 feet, not 50 feet. My unit is never going to perform correctly. It's never going to deliver the capacity it needs to that fan coil. That's why this is so important. This is where 98% of contractors miss the mark. Installation, recording distances, ensuring your line size is correct. If you have to completely relocate a unit, it has to go through this program first before you install it and say, yes, let's put it there, because you might find out the suction line went from 7/8 to 1 1/8. That's a big deal. Sure, 3 feet, not that big of a deal. 75 feet up through a riser to a roof, that's a very big deal. And that's where people usually miss the mark, right? When should we be measuring these pipes, right? So there's the initial design of the system itself, right? We've got a project, we take the drawings, we measure it, we put it into the program. Based upon the drawings, Mr. Engineer, here's your sizing, here's your distances, here's your diameter. Then we go on site and we start laying it out. And we go, whoa, 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 whoa. Did anybody see this steel beam that's going across this building? We got to go up a floor, we got to go down a hallway, and then we can come back into that room. So then you make the change. That change should then go into the report and be reran. You're not doing 3/8, 5/8 anymore. You're doing 7/8 and 1/2 inch. And then last and final, you have as-built, which is where that one person who did the installation has all the numbers that they need. They put it into one specific drawing. We make a final copy and we say, okay, you didn't do the installation, but you're doing the startup. Here is your final copy of the installation that says that system needs 23.8 pounds of refrigerant to start and run, according to the distances, according to the line sizes, all that stuff like that. Let's get in. We're going to breeze through this stuff pretty quickly. This is just the electrical wiring section of it. Every VRF system is the same. It may come in different colors, different flavors, different sizes. Everybody likes to think that they have the secret sauce that makes their brand specific and matter, and on some accounts they do, but they're all pretty much the same. So you have one outdoor unit. That outdoor unit then goes over, and it goes to one fan coil. And that fan coil goes to another fan coil. And that fan coil goes to another fan coil. VRF is different in the fact that we actually use one communication line. You're going to find that common thing in all VRF. It's all one refrigerant line set. It's all one communication line. Everything is daisy chained together. Star communication is not something that we do here. Which means that from my outdoor unit, I go to my indoor unit. And from this indoor unit, I go to my next indoor unit. From that indoor unit, I go to my next indoor unit, to my last indoor unit. and they all talk to each other on the same communication line back to the outdoor unit. On my outdoor board, I can count exactly how many indoor units it thinks it sees. On my outdoor unit, it can count exactly how many branch selector boxes it actually sees. So then if we change this layout and we add indoor units, and these are branch selector boxes, it goes like this. The big misnomer with Daikin is that this is all one big communication loop. Well, it's not really. Indoor units talk to the BS box. That's one communication loop. Then the BS box talks to everybody else on the system. You'll notice here we have F1, F2, P1, P2, T1, T2. P1, P2 is remote controller, right? Let's add another layer to this, right? Remote controller to indoor unit to BS box to outdoor unit. This is one line of communication, this is one line of communication, and the rest are on one line of communication. Why is it we use a 2-wire communication system instead of 24 volts for VRF? Anybody?
Is it shielded?
What's that? Well, sure. Voltage, that's a part of it.
I guess risk of breaking or having like shorts or something. You only have 2 wires, and I guess they only send in signals like they go like bip.
So what's the difference between a communicating piece of equipment and 24 volt control?
I mean, you still have 24 volts. It's just right. You just go like send.
Are you asking me? Or are you telling me?
On and off. I don't
Yeah,
know.
no,
I just
that's
know
fine.
They go on and off,
Yep.
like sending power.
Yep.
You know, like certain amount of time, so that tells the unit what to do.
24 volt control, we're limited by what? The number of wires we have, right? I have one for cooling. I have one for heating. I have one for a fan. I have one for electric heat. Lord forbid I have hot gas reheat. Lord forbid I have a solenoid valve on my liquid line that I have to close. Wait a minute, now I have more temperature sensors, and so it adds up. Are we going to run, 20 wires to one indoor unit to the outdoor unit? It's ridiculous. The reason we don't use 24 volt control is there's too much information that has to be relayed in a timely manner between everybody at any given time to use that many wires. Your electrical panels will be the size of this board, full of ice cube relays to tell it to do something simple and menial. We use 2 wires because we transmit packets of data in binary code that the unit deciphers and understands exactly what it's saying and how. Temperature. My suction line is 73 degrees. My liquid line is 83 degrees. My return air temperature is 72 degrees. My fan speed is this. That information is on repeat 7 times every second for every indoor unit on the same communication line, telling the outdoor unit where I'm at, what I'm doing. Oh, they changed the set point. I need to send that information. Send it, send it, send it, send it, send it. And you do that times 64 indoor units. That's a lot of chatter.
So that comes. How do you program that?
You don't program it. It comes programmed already. Auto addressing. You hook your indoor units to your outdoor unit. The outdoor unit knows exactly what size the indoor units are, where they're at. It gives them a name. Your name is Sally. Your name is Harry. You're 01. You're 03. You're AB3674. It auto addresses them and gives them name and says, okay, are we ready to run? You're good, you're good, you're good, you're good, you're good. Okay, let's run. It does all that automatically. There's no programming. You look at something like this and you go, oh man, like there's no way. I don't have the time. I need a laptop and, I need a degree from MIT. I'm going to have to write this program from scratch. It's plug and play.
There's no setup or nothing at first startup or anything like that.
No? Count your boxes, count your fan coils.
Which train would do that?
Mitsubishi, Train, Samsung, they're stuck in the rotary dial phase, and they just don't want to quit, which is fine.
Yeah. No, they make you install 2 extra wires for the DC communication.
Well, and there's also end-of-the-line resistors, for like backnet and stuff like that. And some VRF systems require end-of-the-line resistors to tell the system, hey, we don't have any more fan coils, stop looking. Daikin does not. It's auto-addressing. Turn it on. If it has power, it will communicate, it will count. If it's wired in. With that being said, let's not get lost in the weeds here, guys. It's just 2 wires, right? System talks to the indoor units or the BS boxes. The BS boxes talk to the indoor fan coils. If you do a count on the outdoor unit, which we'll walk you through when we actually do a startup on these, I hope to have most of you guys there. you'll see how to do that, right? You push some buttons and you say, okay, I have 15 fan coils. My outdoor unit sees 15 fan coils. I'm good to go. If I go to my outdoor unit and I know I have 15 fan coils and it says I only have 13 fan coils, it's like, okay, well, who's missing? And there's ways to put the system in a specific mode to turn all the fans inside on to find the ones that are missing out of the communication loop, right? The ones that can talk to it will turn on and in a fan. I walk inside and I find the fans that aren't running. Those are my issues, right? Look at my unit, measure my voltage. I don't have any. Follow the wire. Okay, it got landed on the wrong spot or it never got ran in the first place. It has its complexities. I'm not going to lie to you. I'll show you exactly what that looks like. But at a basic fundamental, it's just two wires. And they're non-polarity sensitive. So even if you mess it up and you change colors between indoor unit and outdoor unit or indoor unit and BS box, it still knows what it's doing and it knows who it's talking to. So I can go red and black and then I can go on my next unit and do black and red by accident, right? Because I had to go out to my truck and grab a wrench, and then, my wife called me, and then I came back inside. Oh, I got to use the bathroom now. And then I finally get back to that last one. I'm like, wait, did I do red and black, or did I do black and red?
It doesn't matter?
It doesn't matter.
But isn't it 24 volts?
Nope.
It's DC.
DC voltage. 16.5 volts DC. So it's a carrier wave, which eventually I will teach you guys a class on how to use an oscilloscope and what that looks like on that signal, but the carrier wave is 16.5 volts VDC. These up and downs that you see are plus 5 volts and minus 5 volts. These are the data packets that they are sending. You put your multimeter on it and you will never see them because they happen in millisecond increments.
Yeah.
It happens so fast that you will never catch it with the meter.
They actually, I was reading that AC to DC is actually, the other way. It's actually not a real thing. It's just like you have diodes that keep switching, and it makes the unit think that you have DC or AC. But it's actually not doing that. It's just switching diodes to send it.
Yeah, and that's essentially how an inverter works in general. I wrote a tech tip for HVAC school that tells you exactly how the inverter process works from AC to DC and what we're doing and how to check inverter boards and stuff like that. So if you haven't seen it, I can give you a copy of it. It's extremely helpful when you guys are working on systems like this and you're trying to understand that. But this is just the communication protocol. And so there's going to be a carrier wave, which is the 16.5 volts DC. So when I go between F1 and F2, I'm going to see 16.5. If I have a lot of fan coils connected and it's a lot of wire, it might be 15.4. As long as I'm above 14.7, that's all that matters. That 16.5 volt carrier wave is going to then do these plus and minus 5 volt packets in milliseconds that you'll never see to talk to each other. So you're really only concerned about, okay, I can't see that fan coil. It's not working. It's got an error code. U4, which is communication error. Let me check. Okay, 16.5 volts DC. No, I don't have it. Okay, there's a problem.
The F1, F2 is the
Correct.
communication.
Between all the indoor units, yeah.
And that's both inside and okay. So
Correct, yeah. The outdoor unit's kind of shaded a little bit, and I got my trainer, I'll show you, but F1, F2 in on the outdoor unit, and then it's just the F1, F2. And so they're daisy chains. So you have two sets of wires landed if you have another fan coil to go to on that indoor unit. And then outdoor units connected together, Q1, Q2, and then the F1, F2 out, that goes to like a centralized controller, so we can have a touchscreen controller that actually connects to 13 different outdoor units in the entire building. And I can see all the indoor units from one controller. That would be where it connects to on the outdoor unit. And then that in itself is still connected to this communication line. But let's not get bogged down to that. I'm going to teach a service class just on that, but this is the brief overview, guys. So here's that 16 to 18 gauge, right? In the installation manual, it tells you if you're going to go over X amount of feet total length for a specific area that you want to go to 16 gauge wire, not 18 gauge, 2 conductors stranded. We don't use solid core. The pinch, the nicks, the crimps, the twists, the pulls on solid core wire will cause data packets to get lost in transmission, whether it's today, whether it's tomorrow, whether it's a year down the road, you will get communication issues. Stranded wire is the only thing that you can use for communication like this. We're talking data packets in milliseconds. Easily can get corroded, corrupted, changed, look like something else when you use solid core wire and run it close to a high voltage wire. The magnetic interference and frequencies and radiation that's given off from actual high voltage that you can't see actually interferes with stuff like this. Daikin says don't use shielded wire. They've had a lot of problems with shielded wire in the past and recommending it. Brian recently talked about it too, about using shielded wire. I'm a firm believer in shielded wire as long as you use it correctly, and that's grounding it on one side, not both sides, and not creating an antenna. If you ground it on one side, it's good. Don't ground it on both sides. And also, don't not ground it, right? It doesn't do anything. It causes more problems than it fixes. But if you follow the rules and you use this wire, 16 to 18 gauge, 2 conductor, stranded copper, not aluminum, you can use non-shield and not have an issue. I've never seen it become an issue unless you're building it next to a radio tower, and then that's a whole nother bag of cats. Tell you what. Manifolded modules, Q1, Q2 between modules. We shouldn't run into this anytime soon. When we do, we'll cover the topic more in depth and in thorough, but it's just basically a daisy chain wire. They just talk to each other. They have to see each other if they're on the same system. This is what that wiring schematic looks like. Every job that you do with new construction or even retrofit, you will be provided with one of these. You'll know exactly what model number indoor unit, what model number thermostat, what tonnage, where in what position, and how to wire them. F1, F2 here, F1, F2 here, F1, F2 here. Oh, that's P1, P2 there. This is the wiring schematic for VRF. Not wildly complicated, guys.
That's the outdoor units on the left.
Yep. 2 outdoor units tied together, going to all these indoor fan coils with all these controllers. And this is with branch selector boxes. It's just another layer. But you'll see the commonalities there. F1, F2 in, F1, F2 out. All right, last but not least, service manuals. I have every service manual that Daikin makes. I've got a bunch of service manuals from other manufacturers regarding VRF. I know we had to look up a few in the field for LG. This is your handbook, right? I don't know everything. I know, big shock, right? I may have been doing this for a long time, and I understand this equipment very well, but I can tell you right now that I lived and breathed inside these manuals when I was working out in the field for this equipment, because you can't know everything. But I can tell you that everything about that piece of equipment is in these manuals. Where the wires are, what the unit should be doing, what does startup control mean, what is defrost supposed to do, when is it supposed to do it, all that stuff like that. It's all in these manuals. So I'm actually going to get you guys some flash drives with all the stuff already on it so that you just have it in case you ever need it. Or you want to browse through it. We're getting to the point now, too, with a lot of this equipment, like this one here, you'll notice on the right-hand side there is a removal and procedure. So if you ever have to do a repair on the unit, it actually now has a step-by-step picture diagram of what screws to remove, in what order to get to those components, to pull those components out, to put the components back in, step-by-step.
It's on
In a manual.
so you can't.
It says, you listen, Mr. Technician, you're replacing an inverter board today on this particular model. Step 1. Undo 13 screws in these locations.
We're gonna be out of a job soon.
Well, so you won't be out of a job, because what happens is the guy who thinks, the maintenance man who's playing VRF technician, he replaces the inverter board, and then he finds out when he turns the power back on, he's got the same error code he started with. He misdiagnosed it. There will always be the need for human interaction and skill.
Manuals, do they tell you exact voltages you're looking for?
Yeah, error codes, what you should, so let's say it says your compressor's overamping, it'll tell you where to check and what to read voltage-wise. If you're checking an inverter board, what you should be doing in regards to, using your diode test and where your probes are supposed to go and what it's supposed to be if it's good, what it's supposed to be if it's bad.
Because when you're in a field, that's the hardest thing to find.
Yes.
Like you're trying to diagnose something, you know you got a certain amount of voltage, but you don't know if that's the correct amount.
Yeah.
You have to call them.
You're like 32 volts, what the heck
You're
is
sitting
this?
on the phone for an hour just to tell you, oh yeah, that's the wrong voltage. That's your problem.
Yeah, Mitsubishi's about 30 volts DC. So everybody's different.
Yeah.
And some manufacturers, they keep that stuff very closely guarded, and others, they just, there's a reason you need to know it, right? Like the 16.5 volts DC. You should know that, yeah. You should have access to that. Mirror units, a little bit more different design. You'll notice it on the top right there, that's the VRVX that we're going to be doing here shortly. But on the left-hand side, that is the Mirion unit. You'll notice that the service screen actually changed down to the below cabinet there to the left. It is a LCD display screen. Lord help you if you have to work on a VRV3. It's all binary code. So it's just actually flashing lights, which is what I cut my teeth on growing up. It kills a lot of technicians. So listen.
Like count flashes?
Yeah. Well, so it reminds me of the train split systems, the TAM air handlers, right? When you've got the fan board and you've got the control board, and they're both flashing different lights. You've got 3 different lights, right? Previous error code, current error code, and you're sitting there counting like 1, 2, 3, 4, 5, 6, 7. It's the same thing. Newer versions, LCD scrolling display for most VRF2. This is something that we'll eventually get into. This is what we're going to. This is all live. They have a new web-based program for Daikin equipment called the Hero program. I was there when we were developing it and got it to where it is now, but essentially you can see all of these information and numbers and color-coded and flow diagram live off of a piece of equipment remotely. So you get a call from a customer and the customer says, hey, it's not cooling correctly. I can tie into your system live and look at exactly what every single temperature, compressor speed, fan speed, what everything's doing, where it's going, how it's performing, all that stuff like that from my home, right? Service devices. We're going to see a lot more of these guys. Every single VRF piece of equipment takes a different service device. Everybody likes to be special. We have every tool manufactured to service VRF. Some of these we only have 1 or 2 of. Some of them I have 4 or 5 of. As we get into the service side of things and as we start running these VRF service calls, I'm going to train you guys on how to use these service tools, how to interact with these service tools. They do require a laptop. Some use Bluetooth and you can get on an app on your phone. But either way, if you're going to a VRF service call and you don't have the correct service tool, you are flying blind. Hopefully it's a high voltage problem. Hopefully it's a failed electrical component that you can just test with a multimeter. But if the system has no error codes and it's just performing really poorly, how can you see anything? You can't see all the temperature sensors inside. You can't see all the components that go into a system. And so, be mindful, right? Do you have the right service tools for what you're going to look at? No different than if you go to a split system call and, oh man, I left my gauges at home. How effective are you really going to be? You have a multimeter and you're going to go troubleshoot a low voltage call. Well, I guess I'll just keep tripping fuses, right, until I find it. Correct tools are everything. Slowly wrapping up here is for what we look at. This is a typical indoor unit. There's a main PCB control board, right? That main PCB control board has 3 things. Every VRF piece of equipment usually has 3 things. Some just have 2. That's temperature in, temperature out. We measure temperature in and temperature out on every single VRF fan coil, whether it's Daikin, Mitsubishi, whatever. Why is that? Can anybody tell me why that is? Why do we need to know what temperature is coming in and what temperature is going out?
Working around.
To know if it's cooling properly.
How else will we know? We just assume? These have electronic expansion valves that are designed to adjust from 0 to 2,000 pulses, microsteps, to deliver a specific amount of capacity. How does it determine how much capacity it needs? Based upon temperature sensors. If I have refrigerant leaving my expansion valve at a low pressure saturated vapor, it goes through my heat exchanger and exchanges heat and comes out the other side, and I have a 20-degree superheat. My indoor unit then says 20-degree superheat. No, I'm looking for a 9. Open up expansion valve, 25 pulses. Superheat doesn't change. Open up valve, 25 pulses. Superheat doesn't change. Open up 50 pulses. Superheat goes down by 1 degree, it's 19 degrees. Still not close. Open up 100 pulses. Superheat goes down to 15 degrees. Still not there. Open up another 100 pulses. 10 degrees. Okay. Close off 15 pulses and it starts to dial it in. And so it's constantly doing that. And the way that it does that is by the temperature sensors on the indoor unit. Why is it important to know that? The importance behind that is because if your temperature sensor is faulty and it's misreading on its resistance because the sensor is old or it was overheated, someone took a torch to it and cut off the flare fittings because, they're in a hurry. And you know what? I've been doing this for 30 years. You don't have to tell me otherwise. So then they actually, when they talk about that and they go through it, temperature sensors on these units, if they're 5 degrees off, if they're 20 degrees off, if they're anywhere close to that, it can become an issue. The unit thinks that it has a 20-degree superheat when actually it has a 0-degree superheat. What's happening now? I'm getting liquid in my suction line, which is not something we want. So just be mindful. All of these units are using the same exact thing. Just a quick display, right? Why would I have a low superheat on an indoor fan coil? Dirty filter, right? Lack of airflow. It's a heat exchanger, guys. It's designed to exchange heat. What's one thing that would affect a heat exchanger? Insufficient airflow. This is all the fun service data you get to look at. And this is just one snippet. 2,000 lines of data on some of the very large systems, small amounts of data on the other. These are all the things that we're looking at. I compare this to the movie The Matrix, right? At the beginning, you won't know what you're looking at or what it means. But as you progress, as you guys learn, as you go through it, you will slowly make sense of what this information means and how to track it. And we're going to teach you all this stuff like that. So, yeah, I put that at the end just to discourage you as we move forward. This is a wiring diagram. I can't stand it. This is the wiring diagrams they're going to on the newer units. This is what I call the carrier method. Everybody here familiar with carrier package units on the commercial side?
Yes.
Mile long. If this model, no, that's not me. If this model, no, not me. If that model, oh my God, where do these wires go? I just want to get the dang thing running. Why does it go through the economizer and then back again? That makes no sense. That's what they're going to for these wiring diagrams. But it's similar, right? If you don't have that model, cross it out. Don't have that model, cross it out, doesn't apply. But this is a typical wiring schematic for a VRF system. Should be very familiar for you. And we'll walk through that with troubleshooting. The other thing I want to just note, guys, for VRF systems, you don't just go to a VRF service call, put a laptop on it, record 5 minutes of data, and then leave, right? These are systems that are constantly changing valve pulses, temperature, revolutions per second, compressor speed. Things change so quickly, but they also change very slow. And so you can't just go to a system and record 20 minutes of data. The unit may not even start in the 20 minutes, right? It'll stay at low compressor revolutions and startup control before it even takes off to find the problem in the first place. So when you go to a system like this, you have to make sure that you're given the right amount of time. And that's on me, that's going to be on Sam to understand what those time frames are in general. But if you're going to record data, the minimum I say is 2 hours of operational data, turning it all the way on. And you can call me if you're on a call, if you're going to go to a call, and I can prep you for it. I can't tell you how many times I got sent data. Here's 15 minutes of data. Tell me what's wrong. Unit didn't even turn on in the 15 minutes. Like, what do you want me to tell you? Service and maintenance, yada, 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 oil samples, oil, blah, blah, blah. We'll get into all this stuff when we do service classes. Refrigerant leaks, recharges. We don't typically like to top off a VRF system, right? When we measure liquid line sets on a system, it's a specific charge. There's no way to gauge the amount of refrigerant in a system. Sure, there are ways and methods to do it, but there's really no way to be certain, especially if you've never touched the system or installed it in the first place. Pull the entire charge, weigh the entire charge, and then recharge based upon that.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.